Hello, I am Rian, and now I am going to talk about the ILP, the integer linear program to compute the exact solution of the multi-level Steiner tree problem. Using this ILP, we can compute the experimental approximation ratio of different heuristics and then compare different heuristics based on those ratio. So this ILP has this objective and it has this flow constraint which basically ensures that in every level we have a valid Steiner tree. And then this constraint ensures that if an edge is present in a top level, then it is also present in the bottom levels. This constraint links together the flow variables with the edge variables. And finally, this constraint ensures that the edge variables are binary. In other words, it can be either in the solution or not in the solution. Now we talk in details about all the constraints. The objective is to minimize this summation. Here, Ci prime uv is the incremental cost of edge uv with rate I. Hence, Ci prime uv is the difference of the cost E with rate I and the cost of the same edge E with rate I minus 1, and C0E is equal to 0. The variable xuvi is equal to 1 if uv appears in the solution with rate greater than or equal to I and 0 otherwise. The objective basically ensures that in our solution there is no cycle like wuxv. The reason is if there is a cycle, then we can remove some edge and we can get another solution which is better than the previous solution. Now this is the flow constraint and it contains some flow variables. For every edge E equal to uv, we define two flow variables, fuvi and fpui. In other words, the flow can go either from u to v or v to u. The flow constraint ensures that the edges of rate greater than or equal to I form a Steiner tree over Ti, where Ti is the set of terminals for level I. Now we have two kinds of vertices. The black vertices are terminals and the white vertices are non-terminals. We select a terminal as a root vertex. For example, here R is the root vertex. And the total amount of outgoing flow minus the total amount of incoming flow from root is equal to the number of remaining terminals. For example, here the difference of outgoing and incoming flow for R is equal to 3. And as we can see, we have also 3 remaining terminals. Now, if a vertex is a non-terminal, then the total amount of outgoing flow minus the total amount of incoming flow is equal to 0. For example, the vertex U has outgoing flow equal to 3 and incoming flow is also 3. Now, if a vertex is a terminal but not root, then the total amount of outgoing flow minus the total amount of incoming flow is equal to minus 1. For example, consider the vertex W. The total outgoing flow is 1 and incoming flow is 2 and the difference is minus 1. If an edge is present in a top level, then it has to be also present in the bottom levels. And the bottom level may have additional edges also. This is ensured by this constraint. And this constraint links together the flow variables with the edge variables. In other words, if an edge is present in the solution, if and only if there is a flow in the corresponding edge. And finally, the edge variables are binary. It can have either value equal to 0 or value equal to 1. Now we discuss the experimental results. we first discuss the experimental setup. We consider two types of edge coasts, proportional and non-proportional. We consider four types of graph generation: the Erdos-Renyi graph generation model, the Watts-Strogatz model, the Barbasi-Albert model, and finally the Stein-Deeb instances. The number of priorities L varies from 2 to 7. We adopt two methods for selecting terminal sets: linear and exponential. In the linear method, as we go from top to bottom, the number of terminals increases linearly. And in the exponential case, the number of terminals increases exponentially. We now provide a plot where we show the performance of C2A, which is the algorithm from the paper Charikar et al. For non-proportional edge weights. We compare C2A with Kruskal-MLST, which is the Kruskal-based algorithm for the multi-level Steiner tree problem. We denote it by Kruskal-MLST. On Erdos-Renyi graphs, with respect to L with non-proportional edge weights, and L is the number of priorities here. And we consider different values of L, and for a particular value of L, we aggregate all the instances. For example, there are 190 instances for a specific L, and we provide the minimum, the average, and the maximum experimental approximation ratio. And we provide it for both algorithms, C2A and Kruskal-MLST. We can see that the average experimental approximation ratio slightly decreases as the number of priorities increases. And we can also see that the ratio of Kruskal-MLST is slightly lower than the average ratio of C2A. Hence, Kruskal-MLST is performing slightly better compared to the other algorithm. And also the maximum ratio is slightly lower than the other algorithm. We now provide the information in a tabular format so we can make a better comparison. We provide the information for four types of graph generations. And we provide different statistics for both algorithms, C1 and K. Here, C1 is the algorithm for proportional edge cost from the paper by Charikar et al. And K denotes the Kruskal-MLST, or the Kruskal-based algorithm we proposed. We provide how many times the solution is equal to the optimal solution for both of these algorithms. Then we provide the average experimental approximation ratio, the median of the experimental approximation ratios for all instances, the minimum and the maximum. Here, best approximation reports the percentage of instances out of 1,140 that each algorithm achieved strictly better experimental approximation ratio. Best performance in each category is bolded, and as we can see that most of the time the Kruskal-based algorithm performs better compared to the other algorithm. So this was for proportional edge cost. We provide the similar information for non-proportional edge cost also. And here we compare the algorithm C2A, which is the algorithm proposed by Charikar et al. For non-proportional edge cost, and the Kruskal-MLST algorithm. Again, best approximation reports the percentage of instances that each algorithm achieved a strictly better ratio. And best performance in each category is bolded again. And we can see that most of the time, the Kruskal-MLST performs better compared to the other algorithm. More than that, we provide a class of graphs for which the algorithm Kruskal-MLST significantly outperforms the other algorithm C1. Here we can see that the experimental approximation ratio of the Kruskal-MLST algorithm is close to 1, which means that The solution it provided most of the time is equal to the exact solution, almost equal to the exact solution. On the other hand, the experimental approximation ratio for the other algorithm is significantly larger. And here the x-axis is the instance number and carries no meaning of time, and y-axis is the experimental approximation ratio. We now summarize the talk. We showed that the Kruskal-based algorithm is a logarithmic approximation matching the best approximation guarantee of Charikar et al. We formulated an integer linear program for the general multi-level strainer tree problem, which can also handle non-proportional edge cost beside proportional edge cost. We demonstrated that Kruskal MLST compares favorably to other algorithms. A natural question is whether the analysis of any of these algorithms, for example, greedy MLST, Kruskal MLST, or C2A, can be tightened. We now conclude the talk, and we are happy to take questions.